All right, welcome back. This is CSCE 156 and 156H, Computer Science 2. And today we're going to be talking about, we're going to continue with our lists and list-based data structures by talking about stacks and queues. I did want to bring your attention to the fact that Piazza now has a live Q&A feature, which I have enabled for these lectures, and it will be enabled throughout the lecture. And if you have any questions during the lecture, kind of like raising your hand or something like that, feel free to go ahead and post a question in Piazza. Otherwise, if you're watching this at a later date, then go ahead and feel free to post the question as a follow-up later on. Okay. So we already looked at both linked lists and array-based lists last week, or the week, I guess, before spring break. And we're going to continue with list-based data structures by looking at stacks and queues, which are implemented using lists. But the problem with them is that they're unstructured, right? They just hold stuff. Now, lists are ordered, right? But don't confuse that with sorted, right? Ordered is not the same thing as sorted. I could have a list, say 1 or 3, 1 and 2, right? That's not ordered in any. That's not sorted, I should say. 1, 2, 3 would be sorted. 3, 2, 1, that would be sorted in descending order. This is not sorted in any particular order, but there is a first element, there's a second element, there's a last element. So don't think of ordered as the same thing as sorting. In fact, sorting imposes a structure on a list, right? Remember that sets are completely unordered. There is no such thing as the first element, the last element, or things like that. But sorting imposes a structure on a list by sorting it, but it's part of the arrays, or the collections, I should say, collections state, right? Now, remember, in object-oriented programming, an object has identity, and it has state and behavior. The state are just basically kind of like the member variables. And so if you're going to order a list, that means that you're rearranging the internal array, or you're rearranging the internal linked list structure in order to rearrange the elements. That's part of the state. What we're going to be looking at are restricted access data structures. Now, these structures are structures that impose state of the state I should say the structure comes from the behavior, right? With object-oriented programming, again, you have state and behavior. With sorting imposes the state on the imposes a structure on the state, and stacks and queues, they have a structure based on their behavior. In other words, the methods that you can call on them, right? And before we look at that in detail, again, we really like structure. Why? Because structure can be exploited, right? For efficient algorithms and data crunching, data processing, right? Ultimately, that's what an algorithm is doing. It's processing data. And so what we want efficient algorithms, and a lot of algorithms are inefficient, but then they become efficient if you're using a smart data structure under them. Okay? So let's go ahead and take a look at the first one that we're going to look at today, stacks. Right? By definition, a stack is a LIFO data structure. A stack, and you've probably seen stacks before, a call stack, program stack, things like that. But a stack is a data structure that stores elements. So it's a collection data structure still, but it stores them in a LIFO, which is last in, first out manner, right? In other words, the last element to be put into a stack is the first one to be removed from, or retrieved from the stack. That's why we call it LIFO. All right. Now, the way that I usually visualize this is a stack of dishes, right? You've got a dish on top of dish on top of dish on top of dish, and you don't want to go pulling the dish out from the bottom because the whole stack will fall over and break. Where do you put dishes? Well, you put them at the top. Where do you take dishes from? Well, you take them off the top, and that's what a stack looks like. I've got a simple visualization here. Again, you can visualize it as the top of the stack and the bottom of the stack. And this is an initially empty stack. And so if you're going to put something into it, you can push an element and it then goes to the bottom. If you push another element, that'll end up on the top, right? And you can keep pushing until it reaches the top if it has a capacity or something like that, or you can just keep pushing if it's what's called an unbounded stack. But no matter what, whenever you push something, you push it on the top of the stack. You can't go inserting it arbitrarily at the bottom or anything like that. If you did, then you'd have basically a list, right? And that's not what a stack is. A stack is a restricted access data structure. So we're restricting the way that you can put things into this data structure. And we're also restricting the way that you can take things out of the data structure. The reverse operation is called a pop operation, where if you take an element out of the data structure, you're taking the element from the top of the stack. You can't just jump to the bottom and pull the element out from the bottom, otherwise your stack of dishes would fall. You can pop, 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 pop until you reach the end of the stack, until it's an empty stack and you have nothing left. All right? That's the basic idea. So again, a stack has two basic operations. A push operation places a new element at the top of the stack, right? And a pop operation removes and retrieves the element at the top of the stack. Right? And you can have a bunch of other secondary functionality, which we'll talk about eventually here. But before we get into that, let's talk about how you would actually implement this. And again, this entire series, this entire module is list-based data structures. So the easiest implementation is to use a list. Right? And what we're going to do is we're going to use composition. We're going to use composition to achieve this. We're not going to rewrite a list data structure. We've already done that. In fact, we wrote a linked list and we wrote an array-based list, and I'm not even going to reuse those because we already know we wrote those so that we know how they work. What I'm going to do is I'm not going to reinvent the wheel. I'm going to use what's available in the Java standard collections library. All right. Here is my stack class. Let's go ahead and implement this. Now, we need to first think about the state here. The state is simply going to be, not public, but private, a list of elements. Right? And we can call this the underlying list. We can call this a lot of different things, whatever we want to call this. But that's an interface. I'll go ahead and bring that in. Let's go ahead and make a default constructor here. In fact, we don't need to make a default constructor. We can just go ahead and initialize it right here. New. Now, what kind of a list do we want? Do we want an array-based list, an array list? Or do we want a linked list? I'm going to go ahead and go with a linked list for now, and then we're going to discuss why that might be a good decision and why, or under the conditions under which an array-based list might be better. Okay? But we have to use it wisely here. So we now have to define the two basic operations here. Public, void, push, and we'll take an element called item, right? And public, and then we need to return that item, so we'll be returning an element of type T, pop, and of course we won't be taking any arguments here because you always take the one at the top, okay? So what does the push operation look like? Well, if we're going to translate this operation, putting something onto the top of the stack into a linked list implementation, well, we could put it at one end. We could put it at the beginning, or we could put it at the end. Let's go ahead and put it at the end, since that's the easiest. we'll go ahead and add item. Right? Now remember, the add method, that puts it at the end of the list. So if you want to visualize it, visualize taking this and turning it, and turning it clockwise. I forgot how to do that in Acrobat, but you basically just turn it around, and then you look at the list horizontally instead of a top and a bottom. Or the head will end up being the bottom, and the tail will end up being the top of the stack. So by adding it to the tail, then we're pushing it onto the top of the stack. Okay? And that's what we're doing here. So what does the pop operation look like? Well, we just need to be consistent. What we need to do is we need to remove the element at the tail of our linked list if we want the element at the top of our stack. So I'm going to go ahead and store that off. Let's see, elements.get. Right? Now we have to have the index, so whatever the last index is, -1. So this dot elements dot size, and of course -1 because it's 0 indexing, and that gives me the element at the end of the list. Right? That just gets it. What I want to do now is return it, but I also want, before I go back, I want to remove it from that linked list. Okay, and so I can go with elements dot remove, right? And the same one. But if you actually read the Java docs on the remove method, it removes the element from the specified position of the list, shifts any subsequent elements down to the left, subtracts one from their indices, and returns the element that was removed from the list. So we don't actually need to store this off. All I need to do is return that, and now I've got one operation here. Okay? There. Now let's go ahead and see it in action. I'm going to go ahead and create a stack of, say, integers. There we go. And I will go ahead and push elements, say 8, 10, 5, and 3. So at the top of our stack here is going to be the element of 3, then 5, 10, and 8. Remember, it's LIFO, so it's going to be reverse of whatever you put in. And let's go ahead and pop those off. So the first thing that would be popped off would end up being that 3. And then if we popped another element off, that it would be that 5, 10, and 8. So let's go ahead and do that. And so we should have the reverse order here, but of course I'm printing, so I should go with print an entire line so that it looks nice here. There we go. 3 is popped off first because it was the last thing to get pushed onto the stack. 5 is the second to the last thing to have been pushed on the stack, so it gets popped off next. 10 and 8. So in the reverse order than what we push them in. And of course, you can interleave all these operations. You can push 10 elements, pop 5, push another 1, pop another 8, whatever. Push and pop. You can put as many things as you in as you want, and unless it's a bounded stack. Okay. What happens when we pop off of an empty stack? So at this point, our stack looks like something like this. It's empty. Right? I can go ahead and push stuff on this, no problem, because there's plenty of room here. But what if I try to pop when it's empty? So let's go ahead and try and see what happens. I get an index out of bounds exception, which doesn't sound like it has anything to do with the abstract idea of a stack. You're trying to pop off of an empty stack. I should get an error message that says something like that, right? Or I need to rethink about this design, right? So, secondary functionality. Right? You might want an isEmpty method, right? To indicate that this stack is empty. So if you tried to pop off an element, then it's going to result in an error. Maybe you want to introduce a capacity, right? This is called a bounded stack, right? No more than, say, 100 or 1,000, or just in general, n elements can be pushed onto the stack. That's how a call stack works. You have a certain amount of memory allocated to your program for function call after function call after function call. And if you exceed that capacity, then you get a stack overflow, right? So a bounded stack is something where you can only put on a fixed number of elements. It will not grow unbounded, okay? What happens when you try to pop from an empty stack? Right? What happens when you push onto a full stack? That is when you've got a bounded stack. Of course, if you've got an unbounded stack, then this is irrelevant, right? So what happens when you pop off an empty stack, right? Lots of things could happen. We could throw an exception, right? Kind of like what this did, but instead of just an index out of bounds exception, I want a more informative, more germane exception, something that actually references that this is a stack and this is what you did wrong with it, right? Not just that nowhere in my code here do you see me accessing an element within bounds, right? There's no list is under the hood, but that should be completely opaque to us. We shouldn't even know about that. This is a leaky abstraction because it is telling us information about the actual implementation of this stack, okay? So you could throw a custom exception. You could return a special flag value, right? Say, and since we're working in Java here, maybe null, right? Now, there's no right or wrong answer here. These could be, these are design decisions. The first one might be how you want it to behave because of your particular use case, how you're going to use this stack. You could also have a no op, right? Which is no operation, that you fail silently, fails silently, right? It still has to return an element, but maybe we don't throw an exception. Maybe we don't throw give a special flag value. We just give some other weird value or something like that. But no op is no operation. It fails silently instead. All right. So what would it look like to throw an exception? Well, if we want to pop off an empty stack, we have to first check to see if it's empty. So if this underlying linked list is empty, then we cannot pop off of this stack. And so instead of trying to access an element that doesn't exist, I will throw a new illegal argument exception. You can make your own custom exception for this, but I'm going to give it a much better message to the user. You cannot pop off an empty stack. Right? And there's my design decision. So if I run this again, I'll see that now that that weird message is no longer there. It's now that you cannot pop off an empty stack instead. Okay. There. What would it look like if we chose a different design decision? What if we wanted to instead return a special flag value? Right? Oops. There we go. Oh, darn it, sorry. There we go. All right. So I'll uncomment this, and instead of throwing an exception, we can return a null value. Right? And if we run this, now it'll end up printing null instead of throwing an exception, and you'll see that you get a slightly different behavior. Okay. But otherwise, it doesn't throw an exception that it has to be caught. How would we do one of the other secondary functionalities? For example, is empty. If you were going to throw an exception or return a special flag value here, then you need to also give your user the ability to determine, well, maybe I pushed null onto the stack. And so if I'm popping it off, is this the null that I pushed onto the stack? Or is it that I got back null because the stack was empty? You need to be able to give your users the flexibility to make that kind of determination by giving them more interface, giving them more ways to interact with your data structure. So for example, we could say public Boolean is empty, right? And then we could return exactly this up here. If the underlying list is empty, then of course the stack is empty. Otherwise, if it's not empty, then there's stuff on the stack, and so we can return that value there. Right? How might we introduce a capacity here? So, for example, we only want at most 100 elements on our stack. Right? Let me check in over here. Would it be more efficient to try to add the element to the head of the list, since that's the only element that we would be interacting with in a stack? Is there a reason that you would want to go all the way to the tail, or to push or pop an element? Excellent question. It doesn't matter as long as you are consistent about it, and your implementation of a linked list takes care of both ends. We actually dove into the linked list implementation here last week, and we observed that the first and the last element are tracked in Java's linked list implementation. So it's just as efficient to go with the head for all of your operations as it is to go with the tail of all your operations. Now, on our implementation, we didn't do that. We only took care of the head. We never tracked the tail. So it would be inefficient to do everything at the tail, because you would always be starting at the head, traversing all the way to the end just to get that element. Excellent question. The implementation I'm using here, of course, keeps track of those both. You just need to be consistent about it. So if you were going to add an element, then you would add it to the head of the list. Well, if you were going to remove the element, then you need to remove the element at the beginning of the list. And there we've just reversed these. This is now the top of the stack, and now this is the bottom of the stack. All right? Good question. All right? And I'll be checking in over here periodically. All right. Let's make sure that this still works. I didn't screw anything up. 3, 5, 10, 8. 3, 5, 10, 8. That's because I changed both my push operation and my add operation. Okay? So let's go ahead and go back to what we were doing. Let's go ahead and add a capacity to this. So int max number of elements. Right? And we'll go ahead and default it to 100. What you could do there is you could just define a constructor, public stack, and that takes the capacity int max number of elements. Let's say this dot max number of elements is equal to that. Otherwise, if by default, what we could do we could have a default constructor that always defaults to 100 or something like that. Okay, so that I can actually create it down here without having to worry about that default capacity. In fact, I'm going to kick that down to only say 5 elements. So that it's more testable. And you know what? No, I'm not going to do that. I'm just going to make this so that this is a stack of at most 5 elements. And we'll go ahead and push 5 elements on it, which is fine. But if we push that 6th element on it, what happens? Well, if I run this, then of course it's not going to give me any errors or anything. That's because I just introduced this as a number. That number actually has to be used now. So what we're going to do is we're going to check, well, if it's on the push operation, I'm going to check to see if it's full. And the way that I'm going to do that is by simply checking to see how many elements are already stored in the underlying list, and seeing if that's at capacity. And if it is, then I can refuse, do not push the element. Right? And so what I could do is I could throw another exception. You cannot push onto a full stack. Right? There we go. And so now down here, when I have a capacity of 5, but I try to push 6 elements, I'm going to get that exception back here. You cannot push onto a full stack. It's already full. It's at capacity, and I can end up throwing this exception. Well, what about an alternative design? What about an alternative design that, like similar to this, I'll return a special flag value instead. I could say return false, that had no effect on the underlying list, that had no effect on the actual stack. I did not push your element. Of course, if it's successful, you can go ahead and return true. I did end up pushing your element, so I'll return true that it did happen. If you're going to choose that designed approach, then you'd have to have a return type, a Boolean. Right? Since we weren't using it before, we can actually use that now and return a Boolean. Right? And instead of throwing an exception, we can return false instead. And so now if I run this again, I'm not going to get that exception. It's just that that element ends up not getting pushed on. See, 1 was not pushed on, so it was, consequently it was not popped off. Instead, we pushed 8, 10, 5, 3, and 2. That's what the stack looked like. And so when we pop it all off, that's what the stack looks like. That 2 gets pushed off. 1 failed silently. It was a no operation. Right? We can, of course, get that value back by capturing that into a variable, and I can show you that it would have returned false. It did not end up changing the stack. Okay, so a couple different ways of doing that, right? It all depends on your design decision. What do you want to have happen? Do you want it to throw an exception? Do you want it to return a special flag value? It's like null or true, false, right? Or do you want it to just fail silently? Who cares, right? That really only, for the push operation, that really only is germane if you have put on a maximum capacity here. Of course, you could have an unbounded stack by having the default be 0, and then instead of checking to see if the size is there, if the number of elements is strictly greater than 0, that means that you have a capacity and you've met that capacity. So if I don't have a capacity down here, now this is an unbounded stack and I can push as much as I want. And I get all those 6 elements there, all the way down to 1. And true, it'll always end up returning true because it always allows me to do whatever I want with it. Okay. Now, what happens if we say change this to an array list? Let me go ahead and bring that in. Now, because we're using the interface here, this list, then all of these operations don't change. I didn't have to change a single line of code here because I was using object-oriented programming. I was using abstraction. I was using encapsulation. All the details were encapsulated inside of this class, and the abstraction was I was just using the interface of that class. So nothing changes functionally, but something does change efficiency-wise. Now, if I'm pushing everything at the top, pushing everything on the top, I'm always pushing to the head. This is no longer the head of the list. It is now the index at 0. So if there are already 5 elements in there, that means to push it down here, I've got to shift all those 5 elements in there to make room for it. Right? And that means everything is now inefficient. With a linked list, going at both the head and the tail, those were constant operations. But now because I'm using an array-based list and I'm inserting at the head, that means I'm having to shift everything down. And if there are 1,000,000 elements in there, that means 1,000,000 operations. Not only that, but at some point I'm going to hit a capacity. Right? And if I have a capacity, then I can create an underlying array list that is at that capacity. And so if it's 100 elements, I can create an array of 100 elements, and I'll never have to increase or shrink that array. But if I don't have a capacity, if I have unlimited, unbounded stack, then that means that at some point I'm going to fill up that array and I'm going to have to resize it anyway. So there are efficiency issues here with respect to an array list. An array list can be made efficient by simply always working at the end. So if I backtrack this to always that the tail, the end is always the bottom of the stack, and I always keep track of the number of elements in that stack, then I can make it efficient by always working at this end. And removing an element simply means updating the actual number of elements stored in that array or that array list. But again, at some point, you're going to have to size and resize that stuff. So a linked list is generally a better implementation of a stack, but you can make an array-based list efficient. It's just that it's going to be more complex, more design-wise, and therefore you're introducing more points of potential failure in it. Okay, and you always want to keep things as simple as possible. All right. So, other issues would be applications, right? So you already know, you've already seen several applications, of stacks. For example, call stacks, right? In programs. That when a function calls a function, a new stack frame is created. Well, how do you know when the function is done? How do you know to return back to the calling function? You just take the stack frame and pop it off the top, and now the stack frame on top, that's your context for the program. That was the other function that just called that other function. So function on top of function on top of function. It's a way to keep track of breadcrumbs in general, right? Keeping track of what are called breadcrumbs. That comes from the story of Hansel and Gretel. They go into the forest. They're led into the forest knowing that they're going to be abandoned by their parents because they can't feed them or whatever. And so they take along a piece of bread. They need to. They're going to get. They know that they're trying to be made to be lost. So the way that they keep their track of their way back out of the forest is by taking pieces of bread and putting them on the ground so that they can backtrack. They can pick up those breadcrumbs and go back to where they came from. Of course, in the story, birds ate the breadcrumbs, and so they lost their way, and ended up getting lost and going to the witch's place anyway. But that's the idea of where breadcrumbs come from, and so it has a lot of applications in graph traversals. Right? This is a basic DFS, which is a depth first search algorithm, right? And of course, tree traversals. That's going to be one of our future. That's in fact our last module for this course. Are binary trees and binary search trees. It's another data structure that stores stuff in a tree topology instead of a linked list or an array-based list. Well, you have to come up with a traversal strategy for searching through that tree. And the way that you do that is through depth first search. It is basically a depth first search. There's a pre-order traversal, post-order traversal, in-order traversal, and you use a stack for all three of these. And so anytime that you need to keep track of breadcrumbs, then a stack is an ideal data structure to do that. You can also use it to simulate recursion, right? Unfolding recursion. So a lot of sorting algorithms, for example, merge sort and quick sort, those are presented usually as recursive algorithms. But in real life, we don't like recursion because, of course, it's abusing that stack space that you are a function calling function calling function. You can simulate that with an in-memory stack, and most implementations do simulate recursion with an actual stack instead of abusing the call stack to do that. So basically, anytime that you need to keep track of where you've been, so a lot of backtracking algorithms, optimization, right? And this is something that we would cover in, say, Computer Science 3, where you're trying to find a solution or you're trying to find the optimal solution. So you go down one path and you try the solution. Okay, well, you found a solution and it has a certain value or it costs, you're trying to minimize cost. And so it has a certain cost. And so you can backtrack the way that you came and then try a different direction. You're kind of like in a maze. If you're in a maze, you can go down that direction and you can explore it. Oh, that's a dead end. All right, you backtrack to where you were and you go down a different route to find a potential other solution or the way out of the maze. And to do that, to be able to do that, you need to keep track of where you've been. Otherwise, if you don't have any way of keeping track of where you've been, then you could potentially get stuck in a circle. And always have I been here before? I have no way of knowing. So we just have to keep going blindly, going through the maze, trying to find our way out. A stack allows you to keep track of those breadcrumbs of where you've been, so that you don't get lost like Hansel and Gretel did. Right? Lots of applications. There's also a shunting yard algorithm. A shunting yard, it comes from, if anybody has any family members in UP, a shunting yard is you've got a bunch of rail cars, right? In a train, you've got 100 rail cars. Well, this one particular car right in the middle is going to the Midwest, and that particular the one right next to it is going south, and the other another one is going somewhere else. So what you do is you go to the shunting yard where you take you pull the train into a shunt, then you disconnect it, and then you can put car after car after car in there. But when it gets into another shunting yard, then how do the cars come out? Well, the order that they went in the LIFO order. So the shunting yard algorithm is used in a lot of applications. It's used in compilers in order to come up with an expression tree. So if you've got A plus B times C plus D, well, there's an order of operations there that has to be followed. And so it creates this tree out of this expression, and it has to go in the proper order. And so the way that it does that is it uses the shunting yard algorithm. And you'll explore this in lab tomorrow, or whenever you're thinking about doing it, of using a stack to simulate what's called a post order or a postfix notation, where instead of 10 plus 5, you go 10, 5 plus, so that you can push operands. So 10, 5 plus, okay, well, pop, these are my two operations right here. 10 plus 5 is 15. We put that back into the stack, and we continue with evaluating that expression. And you'll see all that in your in lab 11 tomorrow. Okay. All right. You could also have additional functionality. Right. One common thing is, of course, you could get the size, right? How many things are in my stack right now? That's related to whether or not it's full or it's empty. But not only that, I want to know that it's halfway between full and halfway between empty. I want to know actually how many things are in it. You can also have a peek method, which retrieves but does not remove the top element. So that you could just take a peek at it. I want to know what's on the top, because if I were to pop off the top, what element would I get back? And this is additional functionality, because you can always simulate that by popping it. Okay, well, I've got that now, and I'll go ahead and push it back on, and I've got my copy of it to work with, so I know that what's on the top of the stack. Right? So you can many other additional pieces of functionality. You could support arbitrary removal, so that you've got your stack of dishes. Go ahead and pull something out of the bottom. If you really want to do that, go ahead and do that. I'm not going to stop you. But otherwise, then you're shopping for basically a full list rather than just a stack. Okay. Let me go ahead and check in with any questions. Nope. Okay. So again, if you do have any questions, make sure that you're going to Piazza. We've got a live feed started. That's a feature that was recently just added to Piazza. All right, well, that's half of the story. The other half of the story are queues. Right? And if you've ever watched any British television, you know what a queue is. A queue is just simply a line, right? A queue, the word queue is simply a line. And we do not allow no cuts, right? If you line up, then the first person at the head of the line, that's the person to get served. If there are 10 people in line already, you get at the back of the line, and after those 10 people have been served, then you get to be served, right? So a queue, in the context of computer science, is a data structure that stores elements in a FIFO manner, right? That's first in, first out manner, right? So in other words, no line jumping. The first elements are either n-queued or d-queued, right? Sometimes n-queuing is called push or offer. I don't like implementations that call it push, because it kind of conflates that with a stack operation. I do like a offer, but I've not really seen that many implementations that actually call it NQ, even though I believe that's the proper verb, right? So go ahead and queue up, or go ahead and NQ into the line. That's what I like to call it. But basically, you place a new element at the end of the line, right? Now, terminology here, some people call the head of the line the end of the line, because you're the next person to get served. Otherwise, you go to the back of the line, that's the end of the line. I'm going with the end of the line here as being the back of the line, right? So sometimes people call queue, sometimes they call it pop, but otherwise sometimes they call it pull, right? And this comes from service architecture, kind of, that if you're at a bank and you've got a queue, you've got a line that you're being that are being served, then you pull next, next, next. Now, or if people pulled numbers, like we're now serving number 5, right? Number five, where are you? And if maybe they got out of line, they left, they got impatient. Okay, now we're serving number 6. Number 6, number 6. They're pulling the room to see who's available. And basically that means that you remove and retrieve the element at the start of the line. And again, what I mean by that is the head of the line. Right? And as long as you're being consistent about it, it doesn't matter. Again, we're going to use a list implementation. Right? And in this case, I'm still going to use a linked list because the linked list in Java, the Java linked list, keeps track of both the head and the tail. So I can go ahead and insert elements at one end as long as I am dequeuing elements from the other end. You can go ahead and switch those around if you want, as long as you're being consistent about it. But if you work at both work both operations at the same end, then you've got a stack. Right? If you work both operations at the other end, then you've still got a stack. It's just that the orientation is now reversed. Right? So the list implementation, we'll go ahead and use a linked list. Right? You can use an array list, and you can make it efficient for bounded queues, where your queue is at most 10 elements or 100 elements or n elements in general. But you have to be really careful on that, because you need to keep track of what is the head and what is the start. And anytime you get to the end, you have to wrap around back to the beginning. And so it can get very complex, but you can do it. But I'm not going to cover that because it's just as easy, in fact easier, to use a linked list implementation. So I'm going to go ahead and go with a new class, queue, and it will be also parameterized here. And similar to a stack, I'm going to use a linked list implementation. There we go. And the two operations simply just have to be consistent. You can choose one end to be the head or the start or the end of the line, whatever you want, as long as you have, as long as you take from the other end, right? So public void enqueue is what I'll call it, and I'll take the item to enqueue. This dot elements dot add, I'll add it to the end, right? And the dequeue operation, it will return an element of type T, is simply going to work at the other end. The element at index 0. Right? And you need to return that. All right, let's go ahead and create a new queue for integers. And we'll go ahead and enqueue a bunch of things. 10, 20, 30, 40. And then we'll go ahead and dequeue them. And I should get out things in the same order. 10, 20, 30, and 40. Right? Because that's the order that they went in. The first one in is the first one out. The last one in is the last one out, but we don't say LILO. We say LIFO and FIFO. If I have the same issues, design questions as before. What happens when I dequeue from an empty queue? Well, I get an index out of bounds exception. I probably want to check that and throw a proper exception, or return a special flag variable, a flag value to indicate that. Right? So I won't go over all that again. Same basic ideas with the stack as the queue of all those design decisions. Of course, you could always change this. You could always insert at the head, as long as you are removing from the tail. Right? This dot elements dot size -1. That's a little bit more complex code-wise, though, but you get the same exact behavior here: 10, 20, 30, 40. Right? But of course, I'm trying to dequeue from an empty queue. You can have a bounded queue. You can have a peek method. You can have all the things that we did with the stack method. It's just that it's a different restricted access data structure. It's a FIFO data structure instead of a LIFO data structure. It's limiting the ways that you can access the underlying list so that it restricts your ability to pull things out from the allow a line jumper or something like that and pull something out from the middle of the line and serve them first. Although that is a variation, right? Let's go ahead and talk about that now. Queues have a lot more variations than stacks. You could allow arbitrary removal, insert, or retrieval, right? You could allow line jumpers, right? So instead of going to the end of the line, there are already 5 people in the line. I'm a VIP, a very important person. So I get to jump to the head of the line, right? Or maybe I'm a very important person, but not as important as the person that's already in the head of the line. But I'm more important than this person. Maybe I could be inserted somewhere in the middle, right? So you could allow line jumpers. That's called a priority queue, where each element has a defined priority. Whatever your standard for that is, you can define that on your own. But everything has a defined priority, and so you could say, okay, well, where do I need to insert this element? Okay, it has a higher priority than this one, higher priority, but lower priority than this one. Okay, it goes right there. You're allowing somebody to jump into the line according to their priority. This happens all the time, even in real lines. You can buy a VIP pass at Disneyland or something, and go into a different line that gets that has special benefits and less waiting and stuff like that, right? So you can do a priority queue, and it has a lot of applications. For example, you have various priorities that can run in an operating system. Where the operating system priority processes are far more important, otherwise the operating system would grind to a halt and everything would suffer. And so those are given higher priorities. And then user programs, they could have different priorities that somebody that's more important on the system could, in fact, it's called the niceness level. They could set their niceness level to very low, and therefore they have a very high priority, and their processes will get run before all the other processes. Or you could be nice about it and say that, well, this is a database backup, and it should not interfere with normal operations. So I'm going to lower the priority way down so that all those normal operations that are customer facing, those get executed with a higher priority, and my database backup operation down here, that's going to get executed with a lower priority. Only if nobody's online, nobody's using the system at the time, will then my process run. I can be nice about it and set a lower priority. You do this all the time in computing using a priority queue, right? You could also have what's called a deck, right? And again, this is pronounced a deck. It's not a deck queue or something like that. It's pronounced deck, which allows both insert and removal from both ends, right? Kind of like a linked list, right? The way that was, and why that's nice is it's also called a double-ended queue, right? Because you can insert at one end and remove from the other end. It has a lot of applications. For example, I don't have to have 2 implementations, one queue and one stack. I could get away with one implementation of a queue, and it allows you to implement a stack and a queue with one implementation, right? Much more convenient, especially if it's a linked list implementation that has access to both the head element and the tail element. Then you can work both ends, right? But also it has a lot of other applications. For example, you can use a deck to do application undo features, right? So you do an operation 1, operation 2, operation 3. Say that it's Microsoft Word and you're doing an edit. So edit 1, edit 2, edit 3, right? If you want to, I screwed up, I need to undo that. Well, you want to undo the most recent operation. That sounds like a stack to me, right? But you also don't want to keep an infinite number of operations in memory, because then that stack would grow unbounded and eventually you'll run out of memory. So what you do is say keep the last 5 operations. So that if you do an operation, an edit 1, edit 2, edit 3, edit 4, and you do edit 6, instead of overflowing that stack overflowing that stack, then what happens is the oldest one gets dropped off the other end, and now you've got 5 again, right? Here's the newest one, and so it's basically a nice way of implementing a bounded stack or bounded queue where the oldest things get dropped off the first, right? It allows you to bound your queue, but also keep track of the most recent stuff. You can also use it's related to what's called an LRU cache, right? Which is a least recently used cache. So a cache is nothing more than a storage mechanism. You keep things into a cache so that you can look them up easily, so that you don't have to recompute whatever you computed. You compute something, you store it in a cache so that you can look it up later and you don't have to recompute it. You don't have to respend those CPU cycles to recompute it. But also your memory is limited. So if I've got 5 elements here and I've used these 4 most recently, and I've got a new one, and well, this one was least recently used, maybe I don't need it anymore. To make room for it, I'll go ahead and get rid of it, and now I've got an element over here. A deck can help you potentially do something like that. You also have other applications. Right? Well, a queue is anytime you need anytime you need to hold stuff in the order that you got it. For example, buffers. Right? You're probably buffering right now on YouTube. The entire video, you don't have to download the entire video in order to start playing it. You just have to download a small section of it. Then you can start playing it, and then when you get to the end of that buffer, right, it's stored into a buffer, then more data is downloaded so that you can continue uninterrupted. It means that you can download it piecemeal and buffer it as you go along. Then you can jump. That's why it costs sometimes when you jump to another location in a video. It has to redo the buffer, because you have a 1 minute here of play time. If you jump to the next 5 minutes, well, it has to load up that buffer before it can start playing, and that's why there's a little bit of a delay there. But otherwise, anytime you have buffers, right, then that's an excellent thing. Then a queue can be used quite efficiently there. Right. Also, you holding or order servicing requests. Right. Requests may come in asynchronously. For example, a web page. So I've got 50 users on my web page. They're all making requests to my website. But they come in some order, right? And I can't serve 50 people at once. So what I have are called workers or worker threads. And the way that I achieve that is that requests come in. Requests are stored in a queue, right? In the order they are received, and this is basically a buffer. And then workers or consumers, right, are in this context requests, which are producers, then come in, and workers, which are consumers, they take the request off. Look at the queue and take and service a request when needed, right? Or as they are able to. A queue is also an excellent way of keeping track of resources. If you've got a connection pool, we've recently been talking about JDBC and how opening up a connection is one of the most expensive things that you can do. So instead of opening up a connection after connection after connection, you can open up, say, 10 connections up front, put them into a pool. A pool can be implemented using a queue. So I'll go ahead and put my 10 connections into this queue. Anytime somebody needs one, they come and they grab one off the queue. When they're done with it, they can put it back into the queue, back into the pool on the other end. That ensures that it's not just one connection that's being used over and over and over and over again. It ensures that they go round robin. If I've got 10 connections, then the first one will be used, then the second, then the third, then the fourth. It kind of does a natural load balancing by implementing it with a queue. Right? Only when you're done with it do you put it back at the end of the queue, back into the pool. Implementations of pools, of resource pools. It doesn't have to be necessarily a database connection. It could be anything that is resource limited, right? A thread pool, right? And lots of other implementations there, right? So, as you might guess, you don't have to reinvent the wheel. We didn't have to reinvent the wheel on array lists and linked lists. We used the Java implementations, a linked list implementation or an array list implementation, linked list here. And if in practice, that's what you do. In practice, you don't create your own stack or queue, right? In fact, you don't use a stack or a queue in Java. Java provides a deck operation implementation. It's actually an interface. Right? Use it as a stack or a queue or a deck itself. Right? And as you might be guessing, well, what do we have an array-based implementation? Do we have a linked list implementation? And yes, we do. And for that, I'm just going to pull up the documentation here. This is from Java 7, but it's still operable today. Java 12 or 13, whatever you might be on. It's a deck. It's an interface. Two implementing classes are an array deck, so not an array list, but an array deck, or a linked list. A linked list is an implementation of a deck. So if you want a stack, linked list based stack implementation, then use a linked list and treat it as a deck. Something that would look like, what would that look like here? Let's go ahead and replace our queue with an actual deck. Right? And I can't instantiate it like this. That's an interface, but I'll go ahead and pull it in. There it is. And instead of, if I want a linked list implementation, then all I need to do is go with a linked list implementation. Now, they don't have in-queue operations. They don't have dequeue operations. What does it look like instead? Well, that's what this is telling you. If you want to insert at the head of the deck or at the tail of the deck, then you use some of these methods. If you want to insert, then you add first. If you want to remove first. If you want to examine, get first. Or add last, remove last, and get last. And even these have special operations. If you have a capacity constrained deck, then what happens when you try to insert into a full deck? Well, if you want it to throw an exception, then you would use one of these three. If you wanted to give a special value, like return null, or return false, I believe. Yep, it returns false if it's a full already. If you want to remove something and you remove it from an empty deck, then it could return null if it's already empty. And if you want to and of course examine, which is peak operations. So it depends on whether or not you want it to throw an exception or return a special value. You make your choices appropriately. If you want to work at the other end, tail value, then you use, and if you want to throw an exception and you want to insert it, then you add last. If you want it to return a special value in the event of failure, then you offer last. All right? So what does this look like if we want to work from the head on a queue? Well, my queue here is going to add first, and I'll add 10 there. Add first, add first, add first. And if I want to treat it like a queue, I don't remove last. I remove first because I'm going to be working from the same end here. So remove first. Remove first, remove first, remove first. And we can see that this is going to be an exception. A linked list remove first, you can't do that. No such element exception. Instead of an index out of bounds exception, that's nice. But we have 40. Remove first. Oh, sorry, we're doing a stack here. Duh. I want to remove what I want to work at the other end if this is a queue, so it's going to be remove last. Right. We'll go ahead and look at a stack here in a second. And so this should be 10 goes in, 20, 30, and 40, and that's the order that they should come out in: 10, 20, 30, and 40. And of course, if I remove from an empty queue, then I'm going to get an exception thrown. If I want a special value instead, then I would pull last. Pull, not pool. Run this again, and we can see the behavior here that it's going to return a null value, just like my my other design choice of implementation. Well, what does this look like if I want it to be a stack? In fact, we already just did that. This is going to be a deck. It's going to be a deck, but I'm going to treat it as a stack, and I'm going to use a linked list implementation. Of course, you could go with an array deck if you want instead. Let me go ahead and import those. An array deck is not bounded, but you can go ahead and make your own implementation that conforms to this this interface here that is bounded. And I'll go ahead and let's see, s dot. If I want to add to the first, I can. There are push methods, by the way. The queue methods, and there is a push and a pop method, so I don't have to really change anything here. I can go ahead and push, and pop, pop. Right? And then, of course, if I'm popping from an empty one, then it's going to be an exception thrown. It's equivalent to remove first. If I want to remove or pull first instead without an exception, then I can do that as well. I get 2, 3,